We're going to be talking now about reduction-oxidation reactions. Sometimes we call this redox reactions. Redox reactions are going to be electrochemical reactions that are going to involve transfer of electrons in a chemical reaction. Now, before we get into talking about the actual redox reactions, we need to understand something called oxidation numbers. Oxidation numbers are going to be a way for us to keep track of where electrons are at in a redox reaction. Don't confuse oxidation number with charge. Sometimes the oxidation number and the charge are the same, sometimes they're not. That's why we have these rules to assign oxidation numbers. So the first rule, any free element, its oxidation number is going to be 0 for atoms of that element. The oxidation number for any simple monoatomic ion is going to be equal to the charge of that ion. So Cl minus 1, it's got an oxidation number of -1. H plus 1 has got an oxidation number of +1. Only when we have the simple monoatomic ions does the oxidation number equal that charge. Now, fluorine usually has an oxidation number of -1. Oxygen usually has an oxidation number of -2. Sometimes, however, when we have like peroxides, it can have a -1, but most often oxygen is going to be a -2. With hydrogen, if we combine hydrogen with a nonmetal, like when it's combined with oxygen to form H2O, hydrogen's oxidation number is going to be a +1. However, when we combine hydrogen with a metal, hydrogen's oxidation number is going to be a -1, such as the strontium hydride here. Okay, so hydrogen can change. Hydrogen with a nonmetal, hydrogen's a +1. Hydrogen with a metal, hydrogen's a -1. Keep that rule straight. Last thing here, the sum of all the oxidation numbers of atoms in a molecule or ion is going to equal the charge of that particle. So for example, if I have hydroxide ion, it's OH with a -1 charge. Well, the H is going to be a +1, the oxygen is a -2. When I add those two oxidation numbers together, I get that -1 charge. We're going to see some examples of how these are going to work, but keep in mind these rules. They're going to be very, very important. Alright, so let's assign some oxidation numbers. So if I look at the chlorine atom in sodium chloride, what's its oxidation number going to be? Well, it's going to exist as a chloride ion. It's a monoatomic ion, so its oxidation number is the same as its charge. So it's a -1. Let's look at the molybdenum atom in molybdenum disulfide. Well, when I look at this, I have a sulfur. Sulfur is going to be a -2. I have 2 of those, which means the charge on my molybdenum is going to be a +4. It's a monoatomic ion, so charge is going to be equal to the oxidation number. So the oxidation number for the molybdenum is +4. All right, let's look at a little bit more complicated one. I look at the chlorine atom in perchloric acid. What's the oxidation number for the chlorine atom? Now, chlorine typically forms a -1 anion. But remember that chlorine now is part of that polyatomic ion, so it's no longer -1. We actually have to calculate it out. And this is where rule number 6 comes in. So what I need to do is I need to set up an equation where I don't know the chlorine oxidation number, I know everything else's oxidation number, and then I solve for chlorine. So if I have a +1 for the hydrogen and I have one hydrogen atom in that formula, I have an oxidation number of X for the chlorine atom, and then I add that to 4 times a -2 for the oxygen atom, because oxygen is going to be a -2, there's 4 of them, and the overall charge of that HClO4 is 0, so I'm going to set that equal to 0. Well, when I do that and I solve for X, I end up with an oxidation number of +7. That's completely different from the -1 ion that the chloride typically forms. Reason again, it's in that polyatomic ion. Okay, so sometimes the oxidation number is not equal to the charge the ion typically forms. Alright, let's look at another example of this. If I look at the sulfur atom in sulfuric acid, let me set up a formula to solve for it. Got 2 hydrogens this time, so 2 times a +1. plus X, which is a charge on the sulfur, and I only have one of those, plus 4 times the negative 2 for the oxygen. Set that equal to 0. Solve for X. X in this case is going to be a plus 6. So the oxidation number for sulfur is going to be a plus 6 in this case. So what about the chromium atoms and the dichromate ion, the Cr2O7 with -2? What are the oxidation numbers of the chromium atoms going to be? And keep in mind, we want the oxidation number of the individual chromium atoms. Alright, so let's set up our equation. I have 2 times X, X being the oxidation number for the chromium. I have 2 chromiums, plus 7 times the negative 2 for the oxygen. And I'm going to set that equal to an overall negative 2 value because the charge on that ion is a negative 2. So when I add up all the oxidation numbers, they need to equal that negative 2. When I solve for X, X ends up being a plus 6. So each chromium atom has an oxidation number of plus 6. There happens to be 2 of them, but each individual one has a plus 6 oxidation number. Doesn't mean each one has a plus 3 times 2 equals a plus 6. That's not correct. Each individual one has a plus 6 oxidation number. And when we assign these oxidation numbers, we want to assign the oxidation number for the individual atom, not the total number of atoms that are there. Okay, so assigning oxidation numbers is very, very important. It's the first step in what we call balancing redox reactions. So when balancing redox reactions, we have a set of rules for balancing redox reactions as well. Keep these in mind. Use these. Okay, these are steps. They're going to help you get the proper balanced formula. If you want to skip it, you're going to run into problems. Okay, so first thing, whenever you have a redox reaction, you want to identify oxidation numbers for every single atom of every single element in those formulas. Okay, we're going to use those rules we just talked about to do that. Next, we're going to decide what's being oxidized and what's being reduced. Something that's oxidized is going to go to a more positive oxidation number, which means it's going to be losing electrons. So similar to the process of forming a cation, when we take a neutral atom, we lose electrons, we go to a positive charge. That's an example of an oxidation process. Keep in mind, we're talking about going to a more positive value. Doesn't mean we're going to an actual positive charge. A negative 1 is a more positive value than a negative 3. Alright, so keep that in mind. We want the thing that's going to a more positive value. That's what's being oxidized. In the oxidation process, we're producing electrons. Where are those electrons going? They're going to be used in the reduction process. So if something's reduced, it's going to a less positive oxidation number. In order to go to a less positive oxidation number, you need to gain electrons. Where are those electrons coming from? They're coming from that oxidation process. All right, so we're going to look at the oxidation numbers to see what's going to a more positive value, what's going to a more negative value, to identify what's being oxidized, what's being reduced. Once we know that, we're going to write out something called half reactions. We're going to write out an oxidation half reaction and a reduction half reaction. Redox reaction is going to be a reduction-oxidation process. That's why we call it redox. The overall reaction, though, is going to be a component of these two individual half reactions. Once we decided what the half reactions are, we're going to have to balance those half reactions. When we go to balance those half reactions, we need to balance everything but hydrogens and oxygens first, just like we normally do with an unbalanced equation. Next step then, if we have any extra oxygens we need to balance, we do that by adding water. Once we've added the water, if we have any extra hydrogen atoms we need to balance, we do that by adding H+ ions. Last thing we need to do with these half reactions, we need to balance the charge by adding electrons to the side with a greater overall positive charge. We need the charge on both sides of the equation to be equal to each other. Next, we need to make sure that the number of electrons in the oxidation half reaction equal the number of electrons in the reduction half reaction. We can't just add electrons. What we have to do is we have to multiply the half reactions by some integer to get those electrons to equal each other. Once we've done that, then we can add those two half reactions together, and then we simplify by canceling out species that are on both sides of the equation. Right? Those steps are for balancing under acidic conditions. If we want to balance under basic conditions, we're going to go through those same 6 steps and then add 7, 8, and 9 on. So under basic conditions, we balance it under acidic conditions first. Then for every H plus we have, we're going to add an OH minus to both sides of the equation. H plus represents an acid, OH minus represents a base. That's how we're switching it to basic conditions. For every H plus and OH minus we have on the same side of the equation, those are going to combine to form H2Os. Then what we do is we look to see if there's any way to cancel out extra H2Os from the overall equation. Okay, so those are the steps. I know there's a lot of them. Go back and look them over. Keep track of them as we go through these examples. We're going to use those steps now. And we're going to look first at just an easier example of this. So if I take iron solid and react it with nickel 2 chloride, I get iron 2 chloride and nickel solid. All right, I want to balance this redox reaction. Now, in looking at this, you're probably going, well, I don't have to do all that extra work. It's already balanced. You're right. Sometimes these redox reactions can be balanced using the previous method we talked about, balancing chemical reactions. However, we're going to see some that are going to be different, that are going to require these steps that you won't be able to balance doing the normal counting atoms and going back and forth. Okay, so we're just using this one as an initial, simpler redox reaction to walk through those steps. Okay, so first thing we need to do, assign oxidation numbers. So we need to use those rules for assigning oxidation numbers. And what I like to do is I like to write the oxidation numbers above the individual atoms, just so I can keep track of them a little bit easier, and it gives me something visual to look at. All right, next, I need to identify what's being oxidized. Well, remember, oxidized means we're going to a more positive value. So which of those elements in the reactants are going to a more positive value in the product side? Well, that's the iron to iron 2 plus. Iron on the reactant side, 0. Iron 2 plus, positive 2. We've gone to a more positive oxidation number. Okay, so that's what's being oxidized. Now, let's just focus on this half reaction first and go through the steps for balancing those half reactions. So I make sure number of atoms are equal. Well, I have 1 iron on the left, 1 iron on the right. I'm good. I don't have any oxygens or hydrogens to worry about, so I'm good there as well. Last thing I need to do is I need to balance its charge. Well, the charge on the reactant side is 0. The charge on the product side is a +2. So how did I get a 0 and a +2 equal to each other? And remember, I can only get these equal by adding electrons to one side or the other. Well, keep in mind, an electron has a -1 charge. So if I add 2 electrons to the product side, that's a +2 plus 2 times a -1. That gives me an overall charge on that side of 0. So now my charges are equal on both sides. And a quick check to make sure I've got the right thing being oxidized. Remember, the oxidation half reaction should produce electrons, and it does. Electrons are on my product side here. So that half reaction is currently balanced. So now let's worry about what's being reduced. So look at those oxidation numbers again. Which one's going to a less positive oxidation number? Well, that's the nickel 2 plus going to nickel. Nickel 2 plus, oxidation number is +2. The nickel, oxidation number is 0. So I went from a +2 to a 0. 0 is less positive than a +2. Okay, next, make sure the number of atoms are equal. So 1 nickel, those are balanced. I have no oxygens or hydrogens to worry about. Now I need to balance the charge. Well, I've got a +2 on my reactant side, a 0 on my product side, so how do I get those equal? I add 2 electrons. So that should be my overall balanced half reaction for the reduction process. Now to check it, remember in reduction, we're gaining electrons. That means the electrons should be on the reactant side, which they are here. The next step would be to make sure the number of electrons equal each other, which they do. So those will cancel out. And then we'd add those half reactions together. Well, that gives us the overall equation that we see up top. Now you may be asking yourself, what happened to the chloride ions? Well, the chloride ions are actually just spectator ions. They're present, but they're not part of the chemical reaction. So this is a simple example. One other thing to note is we also want to be able to predict oxidizing agent and reducing agent. The oxidizing agent is going to be a reactant that causes another reactant to be oxidized. Well, in order for it to cause something to be oxidized, itself has to be reduced. It has to pull electrons away from something to oxidize it. So the oxidizing agent is the nickel 2 plus. The nickel 2 plus is pulling electrons. Where's it getting those electrons from? It's getting it from that iron. So it's causing that iron to be oxidized. The reducing agent then is going to be a reactant that gives up electrons, causes another reactant to be reduced. So the reducing agent in this case is the iron. So we need to be able to identify oxidizing agent and reducing agent as well.